sheer precipice. Now, by the law of cosmic laziness, which we mentioned earlier, a body coming into the neighbourhood of the hill will not attempt to go straight over the top, but will go round. This is the essence of Einstein's view of gravitation. What a body does, it does because of the nature of space-time in its own neighbourhood, not because of some mysterious force emanating from a distant body. An analogy. Suppose that on a dark night, a number of people with lanterns are walking in various directions across a huge plain, and suppose that in one part of the plain there was a hill with a flaring beacon on the top. Our hill is to be such as we have described, growing steeper as it goes up and ending in a precipice. There are villages dotted about the plain, and the people with lanterns are walking to and from these various villages. Paths have been made, showing the easiest way from any one village to any other. These paths will be all more or less curved to avoid going too far up the hill. They will be more sharply curved when they pass near the top of the hill than when they keep some way off from it. Now suppose that you are observing all this from a balloon. You cannot see the ground, but only the lanterns and the beacon. You will not know that there is a hill, or that the beacon is at the top of it. You will see that the lanterns turn out of the straight course when they approach the beacon, and that the nearer they come, the more they turn aside. You will naturally attribute this to an effect of the beacon. You may think that it is exerting some force on the lanterns. But if you wait for daylight, you will see the hill, and you will find that the beacon merely marks the top of the hill, and does not influence the people with lanterns in any way. In this analogy, the beacon corresponds to the sun. The people with lanterns correspond to the planets and comets. The paths correspond to their orbits, and the coming of daylight corresponds to the coming of Einstein. Einstein says that the sun is at the top of a hill, only the hill is in space-time, not in space. Don't try to picture this. It is impossible to visualize, but it works in mathematics. Each body, at each moment, adopts the easiest course open to it, but owing to the hill, the easiest course is not a straight line. I have given only a description of Einstein's law of gravitation. To give its exact quantitative formulation is impossible without mathematics. The most interesting point about it is that it makes gravitation no longer the result of action at a distance. The sun exerts no force on the planets whatever. Just as geometry has become physics, so in a sense physics has become geometry. The law of gravitation has become the geometrical law that everybody pursues the easiest course from place to place, but this course is affected by the hills and valleys that are encountered on the road. We have been assuming that the body considered is acted upon only by gravitational forces. We are concerned at present with the law of gravitation, not with the effects of electromagnetic forces, or the forces between subatomic particles. There have been many attempts to bring all these forces into the framework of general relativity, but none of these attempts has been entirely satisfactory. For the present, we may ignore this problem. The planets are not subject, as wholes, to appreciable electromagnetic or subatomic forces. It is only gravitation that has to be considered in accounting for their motions. Our third postulate, that a light ray travels so that the interval between two parts of it is zero, has the advantage that it does not have to be stated only for small distances. If each little bit of interval is zero, the sum of them all is zero, and so even distant parts of the same light ray have a zero interval. The course of a light ray is also a geodesic, according to this postulate. Thus we now have two empirical ways of discovering what are the geodesics in space-time, namely light rays and bodies moving freely. Among freely moving bodies are included all which are not subject, as wholes, to appreciable electromagnetic or subatomic forces, that is to say, the sun, stars, planets, and satellites, and also falling bodies on the earth. at least when they are falling in a vacuum. When you are standing on the Earth, you are subject to electromagnetic forces. The electrons and protons in the neighborhood of your feet exert a repulsion on your feet, which is just enough to overcome the Earth's gravitation. This is what prevents you from falling through the Earth, which, solid as it looks, is mostly empty space. The reasons for accepting Einstein's law of gravitation rather than Newton's are partly empirical, partly logical. The new law of gravitation gives very nearly the same results as the old, when applied to the calculation of the orbits of the planets and their satellites. If it did not, it could not be true, since the consequences deduced from the old law have been found to be almost exactly verified by observation. When in 1915 Einstein first published the new law, there was only one empirical fact to which he could point to show that his theory was better than the old one. This was what is called the motion of the perihelion of Mercury. The planet Mercury, like the other planets, moves round the Sun in an ellipse, with the Sun in one of the foci. At some points of its orbit it is nearer to the Sun than at other points. The point where it is nearest to the Sun is called its perihelion. Now, it was found by observation that, from one occasion when Mercury is nearest to the Sun until the next, Mercury does not go exactly once round the Sun, but a little bit more. The discrepancy is very small. It amounts to an angle of 42 seconds, that is, 60ths of a degree in a century. Since Mercury goes round the Sun rather more than 400 times a century, it must move about 1/10 of a second of angle more than a complete revolution to get from one perihelion to the next. This very minute discrepancy from Newtonian theory had puzzled astronomers. There was a calculated effect due to perturbations caused by the other planets, but this small discrepancy was the residue after allowing for these perturbations. The new theory accounted exactly for this residue. There is a similar effect in the case of other planets, but it is much smaller and has not yet been observed with certainty. The perihelion effect in the motion of Mercury was at first the new theory's only empirical advantage over the old. The second success was more sensational. According to orthodox opinion, light in a vacuum ought always to travel in straight lines. Not being composed of material particles, it ought to be unaffected by gravitation. However, it was possible, without any serious breach with old ideas, to admit that in passing near the Sun, light might be deflected out of the straight path as much as if it were composed of material particles. According to the new theory, however, light will be deflected twice as much as this. That is to say, if the light of a star passed very near the Sun, the ray from the star would be turned through an angle of just under 1 second and 3/4. Traditionalists were willing to concede half of this amount. There was a total eclipse of the Sun on May the 29th, 1919, allowing stars near the Sun to be visible. 2 British expeditions photographed the stars near the Sun during the eclipse, and the results appear to confirm the prediction of the new theory. This caused great excitement at the time, but there were many possible sources of error in the observations, and the results cannot be regarded as conclusive. In subsequent eclipse observations, the results have varied between 1/2 and twice the value predicted by the new theory. However, it has recently